Hi there, welcome. Suppose you have a bunch of radioactive atoms, say 12 of them. You know from physics that the time until an isotope decays, let's call this x, is exponentially distributed, with a parameter lambda depending on the half-life of the isotope. You measure for each of the atoms when it decays, and now you want to know what you can say about the value of lambda. Let's wait for the final isotope to decay. No pressure. There it is. Now we can plot this blue curve, the empirical distribution function. Imagine now that we only have this blue curve and we want to use this to say something about the unknown lambda. So to say something about the shape of the orange curve. Well, you know that the expected value of the decay time equals 1 divided by lambda. And by the law of large numbers, you know that the average decay time approaches the expectation after taking sufficiently many measurements. Thus, a good estimate for the value of lambda might be 1 divided by the average decay time. Formally, if you do a number of experiments with results x1, x2 up till xn, an estimate is a function of these outcomes. The important part here is that the estimate can only depend on the outcomes of the experiment and does not depend on the distribution from which the xi are drawn. This is necessary as we do not know the distribution. Otherwise, if the estimate would depend on the distribution, we would not be able to calculate the estimate. If we repeat the experiments on a different day, we get different values for the xi. Thus, the xi are in fact outcomes of some random variables capital Xi. As the estimate depends on the value of the xi, this means that the value of the estimate is also a random variable. This random variable is called an estimator and written capital T. Notice that these random variables xi are pretty special. They all have the same distribution and they are independent of each other. We will call the capital Xi with these properties a random sample. Let's go back to the example of radioactive atoms. 1 divided by the average is an estimator for the value of lambda. But is it a good estimator? To answer this question, we first need to know what we mean by a good estimator. As the estimator is random, we cannot hope that the result is always exactly equal to the real value of lambda. The best we can hope for is that it is close to lambda most of the time. Now, if the true value of lambda equals 10, let's say, then having the rather silly estimator 10 for all outcomes of the experiment would of course be perfect. However, for other values of lambda, this estimator would perform rather dismally. Thus, we need to find an estimator which is typically close to the true value of lambda for all possible values lambda can take. One reasonable thing we could demand is that whatever the true value of lambda is, the expectation of the estimator equals lambda. This means that if you were to repeat the experiment of measuring the 12 decay times many times and calculate the estimator over and over again, your average estimate should approach lambda, whatever our lambda may be. An estimator satisfying this condition is called an unbiased estimator. Suppose you draw from a distribution depending on a parameter lambda. An unbiased estimator for this parameter lambda is an estimator capital T, such that the expectation of T equals lambda for all values of lambda. Notice that for each value of the parameter lambda, the distribution of the outcomes capital Xi is different, meaning that the distribution of T will be different as well. But it will change in such a way that its expectation always remains equal to lambda. Now, let us get back to our estimator of 1 divided by the average. we know that the expectation of the average equals 1 divided by lambda. But since 1 divided by x is a convex function, Jensen's inequality tells us that the expected value of 1 divided by the average is more than 1 divided by the expectation of the average, which is lambda. This means that our estimator is biased. On average, it is too high. How can we resolve this? Well, the average of exponential distributions follows a certain distribution called a gamma distribution. And it can be shown that the expectation of its inverse, which is our estimator t, is equal to 12 divided by 11 times lambda. So if we use 11 divided by 12 times t as an estimator, the expectation of this new estimator u does equal lambda for all values of lambda. Because of this, the new estimator u is an unbiased estimator for lambda. Unbiasedness of an estimator is absolutely a nice thing to have. But how can you decide which of several unbiased estimators is the best one? And besides, is it really necessary to have an unbiased estimator? Or could a slightly biased estimator sometimes be a better choice? In class, you will explore these questions. Before class, I'd like you to think about the following question. Suppose we draw, with replacement, 3 random numbers from the set 1 through capital N, where capital N is some unknown parameter. The probabilities for drawing each of these n numbers are all equal. You can now calculate the expected value of the average of these 3 numbers. And you might already see that this expectation depends on the parameter n. Now, can you turn this average into an unbiased estimator? Or maybe could you think of another way to use these 3 outcomes to estimate n? See you in class!